Okay, as for C, which is C, the question is that motor speed at full load condition if adjustable resistance is 120 ohms. So we take a look at here. If this field resistance is adjusted to 120 ohm, means that we can adjust this 165 from maximum of 165 reduced to zeros, but we adjust down to 120 ohms. So what happened to the motor speed? The speed at full load. Speed at full load, how much when the resistance is reduced to 120 ohm? So what we need to do is that we find the new IF, because once we change the resistance, the current amount that go through into the field area also will be different from earlier stage. So V over RF. So we get the new RF of, so IF new is equal to VF, V is still the same, and divide by RF new, which is 120 divided by 120, so we get 1 ampere actually. Then we go to the magnetization curve with the 1 ampere here. 1 ampere, we plot the graph. So we shall get from our curve 1 ampere, so it goes to 245 like that. 1 ampere, we go to 240, 250, so 245. So we shall get 245 in terms of the new EA. Then we can calculate the speed of full load. It's equal to EA full load divided by EA naught times N naught. So EA full load was 212.5 previously. EA naught we have now 245. EA new year 245 times the previous N naught of 1200. So this is the new speed. Of the motor at full load condition when the adjustable RF reduced to 120 ohm. So in general you can pause this screen and write down, or you can duplicate this answer to your sheet. Okay, next we move to DC shunt motors. So this is DC shunt motor. DC shunt. Okay, shunt means that we have a terminal voltage of the armature current and also the field current. They will share the same terminal voltage. Means that all are connected in parallel. This is shunt. So, okay, as I told you before, the most important is that we know how to redraw the schematic of specific motor that involved in our analysis. So for shunt, you should be able to draw this shunt here. So from the schematic, we can apply KVL and KCL so that we can produce the related equation out of it. So first of all, the field current. So field current is VF. VT and VF are the same. So VT and VF are the same over RF. So VF over RF. Usually we combine R adjustable with RF. So it will produce your IF. Or if we separate, so we have to add up RF plus R adjustable. So this is the amount of value of IF. Then VT, and apply here the inner loop. VT is equal to EA plus IA, yeah, IA and RA. So that's second equation. Then we apply the same to the KCL. So IL is equal to IA plus IF. Because IL here is separate into two. Half go to armature, another half go to field. So IL equal to IA plus IF. So we have three equations derived from the schematics. Okay. Then we further analyze the shunt motors here based on the circuit itself, schematic. We should take note that there's a governance equation of the behavior for this shunt motor, which is omega m, means that the speed of the shunt motor is equal to Vt divided by constant phi minus armature resistance divided by constant phi as well squared times induced torque. So what's stated here, if we plot the behavior characteristic of the shunt motor, we shall have a, this one is your speed, this is your torque. Speed versus torque. So this is the behavior of your shunt motor. So in order for speed to respond linearly with the torque, yeah, to respond in linear, means that when the speed increase or the torque increase, the speed will follow in a linear term, linear trend. So we assume that the incoming Vt here should be constant. Usually if we attach some load to the source, If the load is very heavy, so the VT tends to drop, and it tends to drop. But for this kind of trend, we expecting, or we assume that the VT is fixed and or assumed to be constant. If it's not constant, so the voltage variation will affect the shape of the torque speed curve. It means that if you plot inside your experiment, you can see that if the speed is reduced, the linearity of the graph will be deviate. So it's some sort like you're having further steep of the shape. It's no more like a constant little bit of reduction, but much more like it reduced a lot, and the steepness or the reduction is much observable. And you put more torque, the speed will reduce so much. But if the source of the terminal is stable, constant, so the reduction is not so much. Means that the speed regulation will be stable instead of when the voltage drop, so the speed regulation will have a much effect. Okay, another effect that affect the motor, also the torque speed, the armature reaction. So when the load increase, we put more torque to the shaft, the flux weakening effect will reduce flux. So we can see if the flux reduce here, this is the flux. If the flux reduce, so the speed will tend to increase. By right, if we put we increase torque and we increase torque, the speed will reduce. Okay, it's normal. But what happens that when there is armature reaction, AR, when the armature reaction happen, the flux tend to reduce. So if you reduce by square here, flux square, so the speed will increase. So the speed will no more tend to be in a linear mode with induced torque, but sometimes, certain times, it tend to increase. So we don't want this kind of issue happen or trend happen, because we are not able to control the speed of the shunt motor. So the shunt motor will be much more like a haywire kind of trend. It reduces linearly, but after certain time tend to increase. So this is not preferable for a DC shunt kind of action. So like what stated here, if a motor has compensation winding, of course there will be no flux weakening problem in the machine, and the flux in the machine will be constant. So if there is no AR and armature reaction, we shall have a linear response. But if there is an AR, so the flux will reduce, but in terms of speed, it will tend to increase. Okay, on the next slide, we shall go through on the analysis of the non-linearity of the DC shunt motor. Okay, we'll meet in the next slide.